Hello, this is Mr. Groven, and the topic today is measuring motion. Now, as we go through the video, if you need to pause at any point to write down the information that you need, go ahead, hit the pause button. I do not mind. But I'm not going to pause myself, so I'm going to leave you to write down or look at the objectives and check to see if we get through every single one of them. Okay, now first off, motion. Observing motion by using a reference point. So the first thing we're going to do is define what motion is. And as you can read right there, an object's change in position relative to another object or reference point. Okay, so what exactly is a reference point? The object that appears to stay in place. Now, the reason why we say appears is because, well, you're on Earth and you are on a big ball of clay that is hurtling through space at multiple millions of miles an hour. So you are always in motion. The only way that we can actually measure motion is by relating it to another object. Now, since everything on Earth is moving, well, we just make things a little simpler. We just pick objects that appear not to be moving, like, for example, the creepy tree. Okay, so let's take the little instance here of our little dune buggy, or little car, running down the highway. Now, the tree appears not to be moving, and relative to the tree, the car, this thing right here, is moving possibly at about 25 miles per hour. Now, if we have, going the opposite direction, a guy walking down the road, he's probably walking at a pretty good clip, let's say 5 miles per hour. So in reference to the tree, the guy is moving past the tree at about 5 miles per hour. Now, what if we got the car and the guy walking down the road at about, well, in the same general direction? The car would be moving at 25 miles per hour, but relative to the guy who, as we mentioned earlier, is moving at 5 miles per hour, the car would appear to the pedestrian to be going at about 20 miles per hour. So all we're really talking about is reference points. How fast or what kind of movement is happening in relation to a reference point. And when we're talking about common reference points, we're pretty much talking about any point on the Earth's surface, be it a tree, some poor guy along the road, or, oh, I don't know, say a park bench. No, I'm not going to try and draw a park bench right now. Okay, so let's continue on. Now, this time I'd like to talk about speed. Speed is going to depend upon two values, distance and time. I'll highlight this up here. So speed is always going to depend upon distance and time. Let's get a definition for speed over here. Speed is going to be the distance traveled by an object divided by the time it takes to travel that distance. So we could come up with a mathematical formula. Speed, whoops, let me get a better color there. Let's go for white. Speed is equal to distance divided by time. And in science, our speed is going to be measured in the SI unit, meters per second. Now, I know most people are used to miles per hour, or in other countries you're used to kilometers per hour, but the most used one is meters per second. Okay, now let's take a look at a graph of speed. In other words, a time versus distance graph. Okay, now let's see. In this case, we are Canadian, so we are moving, or we are measuring hours versus distance. Let me get a different color there. Let's try, oh, not red. Let's try kind of a little blue here. So, time versus distance. Okay, so as we move along the graph, you'll notice that there are two lines. There is my red line. I'll try to highlight that here. So we got our red line here. And you'll probably notice that the red line is straight. That's our average distance, or our average speed. But the reality is this little blue line. Let me see if I can't get a different color there. let's try kind of a highlighter red. Our blue line, on the other hand, fluctuates. It goes up, it goes down. Say maybe at this point where it gets a little lower, you stopped off at the gas station, bought some drinks, bought some pop. Then at about this point here, you went a little faster than normal because well, either it was legal for you to go faster or you just wanted to make up for some lost time. So the actual distance versus time is going to fluctuate, while the average is going to stay pretty steady. Okay, let's move on to the next page. Now, I don't have a lot of topics here. I just want to make sure we get through everything. Now, velocity. Okay, now, didn't we just talk about speed? Speed is your distance per time. Velocity is actually pretty much the same formula, but there is one small difference. Velocity is the speed of an object in a particular direction. Let's take our car again. Now, you notice this little compass rose that I got down here. So, see if you can figure out which direction is my car going. Can you see it? The car is going in an easterly direction. Now, I can say, it's going actually in a northeasterly direction, so my velocity of my car is probably 55 miles per hour northeast. Now, once we change direction and it's going straight up, kind of a little up and down here, still going at 55 miles per hour, so the magnitude of the velocity hasn't changed, but now the direction has changed. Now I'm going 55 miles per hour north. And then, of course, this way would be northwest, north again, pretty much east, and as you go along the road, you're changing direction. Therefore, even though your speed is the same, your velocity is changing. Okay, so I want to talk about a couple of other things. Two values. The scalar quantity, which is magnitude only, that includes things such as your speed, mass, distance, whereas a vector is going to include magnitude and direction. Now, in this case, we're talking about velocity, acceleration, and force. So just kind of remember the two quantities. A velocity is going to be a vector quantity, which includes, let's see, get my little vector up there. The vector quantity is going to include your magnitude and direction. All right, now let's continue on to our next topic, where we're still talking a little bit about velocity. So what happens when we change our velocities, or when we have two separate velocities? Okay, so let me show you how that works. Now, we've got this little situation here with a bus. Okay, so we got a man on the bus who is traveling in an easterly direction, right here. And the bus itself is also moving east. Now, the man, he's walking up the bus 1 meters per second east, and the bus is heading 15 meters per second east. So, from the standpoint of the creepy tree outside, the person is going at about 16 meters per second east. So what if he's going the other direction? 1 meter per second west. In other words, he's going the opposite direction as the bus, where the bus is still going at 15 meters per second east. Well, in this case, the resultant velocity is going to be the subtraction of the two values. So according to the creepy tree outside of the bus, the man is actually going 14 meters per second east. Okay, now the last topic for today is acceleration. And acceleration is going to be defined as the rate at which velocity changes over time. So let me give you a mathematical formula for acceleration. My acceleration is going to equal to the change in velocity divided by the time. Okay, let me explain this little symbol right. Give me a second here. Okay, let me explain this symbol right here. Now that's called a delta, the Greek letter delta, and what that means is change. So a full formula would be acceleration is equal to, oops, sorry about that. Erase that A, get you a better idea. Acceleration is equal to your final velocity minus your initial velocity, all divided by the amount of time. All right, let me bring up another quick value, how to calculate average acceleration. Now, if you'll notice with this little script that I just put up here, our bicyclist starts out going at 1 meter per second. Now, about 2 seconds later, he is going at about 2 meters per second. 3 seconds later, he's up to 3 meters per second. So basically, every single second, he is accelerating. Now, if we were to figure out what the acceleration is, what we do is take a little formula, acceleration, okay? Now it's going to equal to the final velocity, which is this one right here, 5 meters per second, minus the initial velocity, and that's, oops, sorry, that's right here. 5 meters per second minus 1 meter, well, no, I take it back, because this guy actually started at 0 meters per second. So if we take the 5 minus our initial, which of course is 0, divided by how many seconds that he was actually traveling, 5 seconds, then you're going to end up with the value 1 meter per second per second. Okay, so that's going to take me up to our next topic here. Let me get rid of some of the stuff here. We don't need this anymore. And I think, oops, no, I want that to stay. There we go. Okay, and I'll take away some of this junk up here too. Okay, now we don't have a lot of time left, so I'm going to continue. Oops. Okay, so the values or the units for acceleration is going to be meters per second squared. So whereas velocity was meters per second, since acceleration is equal to the velocity divided by time, then it's going to be meters per second squared, and that's our common unit. Okay, let's see. Oops, nope, sorry, not ready for that note yet. Okay, so I'm going to bring up a quick graph showing acceleration. Okay, now whereas the previous graph was a graph of distance per time, this new graph is velocity divided by time. So we start out at 0 here, 0 meters per second, and over time the velocity is steadily increasing. You can see this red line right here. So it's increasing from 0 meters per second all the way up to 25 meters per second, and then it's going down again. So what you see here is acceleration and deceleration. Okay, now I'm going to take one last slide, because we've actually gotten through most of the stuff that we needed to get through. The last thing I want to talk about is circular motion. Oops, sorry, got a bunch of scratch marks on the day. There you go. Okay, so circular motion. In other words, what's happening to the acceleration in this weird little, oh, let me get rid of this, in this little cartoon right here. So we've got a yo-yo going around in a circle, and in this case, the velocity, it's a constant acceleration, but the velocity is always changing because velocity depends upon two things, speed and direction. Okay, and that's all I have time for. Thank you, and catch you later.